The next speaker does not drink coffee, but is made up of equal parts pizza and ice cream. I'm happy to introduce Jared Lander.
All right. Thank you very much, Kaz. It's been a pleasure knowing you through all these years as well. So, assuming everyone can see my screen here, and great. So today, I'm going to talk to you about using GPUs with R. So that means we're going to talk about Bitcoin. Okay, all right, just kidding. We're not going to talk about Bitcoin. I had to do that. What we're really going to talk about is Dogecoin. All right, that's the last one, I promise you. We're not going to do that again. We're going to talk about GPU for scientific computing, particularly stats and machine learning. So when I say that, I don't mean just deep learning. There's many other things besides deep learning we could use the GPU for. And we're going to dive into many of those things we can do. So before we can do that, though, we have to ask, why the GPU? Why am I giving a whole talk about GPU? Why are people so excited about these things that are meant for video games? And it all comes down to cores. A typical CPU might have 6 cores, 12 cores, 20. If you have a really great expensive CPU, up near 100 cores. But a GPU can give you thousands of cores. The price per core is lower, and this allows you to massively parallelize your work. You might ask, why can't a CPU have thousands of cores? That's because CPU cores need to be general purpose, whereas GPU cores, each core is doing the same thing at the same time. Well, different times maybe. So they're different types of cores. So you couldn't just get a CPU with thousands of cores. Then you might fairly ask, well, why do we need so many cores to begin with? Why do we need so many of them? What are we going to do with them? For me, particularly, it's going to be programming and machine learning. For programming, that mainly means, in my context, matrix algebra and massively parallel loops. And for machine learning, that could be deep learning, boosted trees, or even Bayesian methods. Yes, we can speed up Bayes using a GPU. So let's see what's available to us on CRAN. CRAN has a whole task view system that's a human-curated system of different packages to use for different use cases. And it lists for the GPU, GPUR, GPU tools, Gmatrix, Magma, and a few others. So let's take a look at some of those, like GPUR, that was removed from CRAN, and GPU tools that was removed from CRAN. Gmatrix was also removed from CRAN. Magma was removed from CRAN. RPUD removed from CRAN. CUDA Bayes Reg removed from CRAN. It looks like they haven't updated that task view in a while, and all that's left are OpenCL, PermGPU, Torch, and Keras. And Torch wasn't even listed. I just added that to the list myself. Bioconductor has a few more GPU packages, but my world mostly lives in CRAN, and it's very hard to use a GPU package on CRAN. Only out of these 4, only OpenCL is general purpose. Of course, there are more options not on CRAN and not on Bioconductor, and we'll look at some of those. But before we can do that, we need to install CUDA. This is a general purpose programming toolkit for computation on a GPU, specifically an NVIDIA GPU. I actually just saw today there was some research about porting CUDA code to a RISC-V processor, but it's very difficult to do. Also very difficult to do is installing CUDA. Now my company is an NVIDIA partner, and I still have a very hard time installing CUDA. You need to install the correct Linux headers, download a PIN file, fetch a GPG key, add an app source, and finally install CUDA, which also installs NVIDIA. It's a lot of work, and I had to patch together these instructions from many different sources, including the official NVIDIA instructions, which led to a lot of bad alleys for me. You might just want to use a pre-built Docker container or a cloud VM. Your life might be a lot easier. For now, we're going to focus on programming and machine learning, and we'll start with programming. We'll look at different frameworks for writing custom code on the GPU, and the first one we see will be OpenCL. This allows you to write generic code that can run on different devices. It can run on a CPU, run on a GPU, an ASIC. Different ways to do this. Before you can use it, you need to install both a Linux library or a Windows library. It's OCL ICD OpenCL dev, and then install the R package OpenCL from CRAN. Once you have everything installed, and by the way, this assumes you have your GPU software installed underneath, you then can go ahead and write your first OpenCL function, which is actually not a function, but a kernel. So we put __ kernel in front of it. The return type has to be void because it won't return anything. It'll actually put whatever your output is in the first argument, which we're calling output, which is a numeric vector, and it's global because it's a memory buffer. That's why we put __ global in front of it. The second argument has to be the length of that output. And then you could give further arguments like your inputs, which can either be a scalar, like in length, or a vector. Now, when I call it a vector, it's actually a memory buffer. And I call it a memory buffer because it's generic. It can live on any memory source. It can be a memory buffer on the GPU or on the CPU. And then you write your function. Right here, I'm building a distance function. But notice there are no for loops. Usually, if you build a pairwise distance function, you need nested for loops. There are none. Because I set I to get global ID, and that knows that there are outlength outputs. And it will automatically parallelize your code across the GPU or other device. So we get to write our code, the last line in there, vectorized. It looks a lot like our code. It looks like vectorized R code. And it's all taken care of for us. The parallelization will be taken care of for us. Now that we have our function written, we actually need to set up where it's going to do the computation. So we open up the OpenCL package, and we look up the platform, which in our case is NVIDIA CUDA. Given that platform, we have a device. It's an NVIDIA GeForce GTX. It's a gaming GPU. And then our compute context will be on this device with that platform. And that's how we create the CTX with OCL context. Now that we have that, we can make the kernel available to us in R. So we call OCL simple kernel. We give it the compute context, the name of our kernel, which has to be the same as the name in the code you wrote, and then the actual code as a character string that we wrote on the previous slide. Now I'm going to generate some random data just so we have something to work with here. And we generate 2 vectors of random normals. I would have liked to put this in a matrix, but this function required it to be a vector, and I could have written the input and the output to be a little bit different, but for ease, I just made 2 vectors. And then I convert these R vectors into CL buffers because it's a memory mapping. Yes, we're duplicating the data in memory, but we have to live with it. We can then pass this data along with our kernel into OCL run, and that will run the kernel for us on the data. This gives us back the distance matrix, and it works. Now, you are limited to GPU memory, so make sure you have a big enough GPU for your data. And OpenCL can be a little clunky, and you're limited to vectors, so it's a little difficult to use. So I want to turn to something that I find a little bit easier, Rcpp Arrayfire. This is like Rcpp, but for the Arrayfire library. This is a tensor library for GPUs. And tensors are just arrays, so we are essentially doing matrix multiplication. It's like Armadillo for the GPU, and the code is mostly vectorized like regular R. To use this, you first need to install Arrayfire, which you could do by downloading the shell script and then executing it with sudo permissions, and then putting the location of this executable, this binary, into a config file. So there's a lot of ways to do this. You could do it with apt, but that didn't work for me with many tries, so I switched to the shell script. You then need to install the R package, but it's not on CRAN. So you use drat to set up Takana's GitHub profile as a repo and install Rcpp Arrayfire from their repo. And now we can write functions that look a lot like that are C++. You do that with normal Rcpp syntax. You tell it you want the Rcpp Arrayfire library, and you declare a function to have an AF array output, which is essentially like an R array. And the input is going to be an Rcpp Arrayfire array, which is a lot like a R array or an R matrix. I'm writing a distance function again, so I have 2 loops. I could have unrolled these double loops into a single loop, but for ease of coding, I just made it 2 for loops. You'll see the first for loop is G4. That's actually a parallel for loop that's going to be run in parallel on the GPU. And I'm going through each row of the matrix in parallel, and for each of those rows, I will sequentially check all the other rows against it. Again, I could have wrote this with a single parallel loop, but just for ease of illustration, I did a nested for loop. And you can't have nested parallel loops. You can only have one nested loop. So then I create some data with a matrix, a 2-column matrix, and I call this distance function I wrote, and it gives me back an answer. You still have to move the data from the CPU memory to GPU memory, which isn't awesome, but is doable. Now, the big problem is this package, Rcpp Arrayfire, hasn't been updated in 6 years. So that might give you pause using this. So rather than writing external code, let's write our code. All our matrix algebra calculations depend on a linear algebra routine, typically Atlas, OpenBLAS, MKL. So NVBLAS is a CUDA matrix algebra library that is a drop-in replacement for whatever you already have on your computer. And then you could use regular R functions on the GPU. To do this, you need to set up a config file, telling it where the log file is, where your CPU BLAS is, which GPUs to use. Well, that's fine. Then when you launch R, you set environment variables like LD preload pointing to NVBLAS, and you point to the config file, and then you launch R. There's a way to do this of RStudio and RStudio Server, but I'm doing this just at the terminal for now. I was inspired by Yaron's talk to do everything at the terminal. So then you create your matrices. I create an A matrix and a B matrix, and I transpose A and multiply it against B. Now, this all happens on the GPU. When you create the matrix, it gets loaded in GPU memory. When you do the multiplication, the GPU is doing the calculations. All for you, nothing's in CPU right now. If you want to calculate the distance of a matrix, you create the matrix. It lives on the GPU. You call the dist function, the same dist function you would use in base R, but now the calculations happen on the GPU. You didn't need to write any special code. It all happened for you. And that's pretty nice. But I like to see what we have next. It's Torch. And it's not just for neural networks. It's also a general purpose matrix algebra library that's been highly optimized. And I think it's going to be easier to use than the regular R functions because you need to worry about the BLAS. With Torch, you don't need to worry about that. So you install Torch, the R package, which is on CRAN, and then you use the Torch package to install the Torch libraries. And type 11.1 means use the GPU. It's using CUDA 11.1. Then I could just check is CUDA available, and if it is, you're good to go. Now, this might not work great if you're using REMV. You have to jump through a few hoops to make that work. So repeating what we just saw in base R, I'm going to create some random normal matrices using Torch normal, and I'm going to move them to the GPU using $CUDA. There is an argument to Torch normal to put it straight onto the GPU, but I'm getting a weird bug that I've been able to replicate on a few different environments. So for now, I use $CUDA to move it to the GPU. Now that my two matrices are on the GPU, I could transpose them by using $T, and then do matrix multiplication with matmul. That's it. Same idea we saw with base R, but using Torch. If you want to fit a distance matrix, I create a matrix in Torch on GPU memory, and I call it Torch pdist instead of the base R function dist. Works great. You are limited to GPU memory, and you typically have less GPU memory than CPU memory, but it's really great and it's really fast. So what have we learned so far about programming? Is that you're mainly going to be doing matrix algebra, and you should really just use Torch. It's the easiest and fastest, both in terms of computer time and human time. So I recommend that even over using NVBLAS from base R. So now let's turn our attention to machine learning. And we'll look at a few methods: deep learning, boosted trees, and Bayesian regression. And we'll pick up where we left off with Torch. We're going to use this for deep learning now. We'll start with the credit data out of the model data package, and we'll make sure it's a Tibble. And our goal for the rest of the talk will be to predict status. So like a good data scientist, we'll use our sample to split it into a training set and test set. And like a bad data scientist, we're going to use a test set as validation also. We then write a recipe to prepare our data, and we're going to write a different recipe for every single method we're using. For Torch, we're going to impute missing data. We will standardize our numerics. We'll turn our categorical data into dummy variables, even though we really should do an embedding. For now, we'll just use dummies. And we need to make the output an integer with 1 and 2. Those are the two levels, 1 and 2. We then use a Torch dataset. We create a Torch dataset, I should say. This is going to have an initialization step that will take our data and do the pre-processing, turn it into Torch tensors, and it creates a function for slicing through individual parts of the data. The data still lives on the CPU. We haven't moved it to the GPU yet. We'll get to that later. We initialize the torch dataset, and then we use a torch data loader that is going to allow us to iterate through. We don't fit the model on the entire data at once. We fit the model on 64 rows of data at a time, or however many rows you want. We are going to do 64 rows of data for our case. Now that we have our data loader, we design our neural network. This is a fairly simple one, yet it's still kind of complex. We have 3 hidden layers. We use the ReLU activation function because deep learning is just matrix algebra again and again. All of the power comes from the activation functions, which gives you nonlinearity, leading to extreme nonlinear modeling. We also define some dropout, so we have some regularization. And this is our model. It took a bit of effort to build this. Now that it's designed, we actually have to instantiate it. We tell it how many nodes in each hidden layer, how big the data coming in is, and we sort of compile. We're not literally compiling it, but we're getting it ready. We then take our model and move it over to the GPU with $CUDA. We are moving the weights over because these weights are giant arrays of numbers that we're going to matrix multiply, and that's all going to happen on the GPU, so the weights now live on the GPU. We then iterate over our data. We need nested for loops. We make multiple passes or epochs over the data, and then we make multiple iterations on the data within each epoch. We do 64 rows at a time. So each time we grab 64 rows, we move those 64 rows over to the GPU with $CUDA. We do this because we only want a little bit of data on the GPU at once, because you're doing these giant matrix calculations. It's going to take a lot of memory. You don't want to put all the data on there. We do this for the training set. We do it for the validation set. We do it for both the predictors and the outputs. Move them all to the GPU and then do the matrix multiplication. Torch models where the matrix multiplication happens. Now, this was a lot of boilerplate, double for loops. Luckily, there's an easier way. The LUZ package, which is on CRAN, it handles it all for you. It handles the validation, it handles the epochs, iterating over the data. You set it up with your optimizer, with your loss function, any metrics you want to calculate. You set your parameters, like the different sizes of the hidden layers, and you are ready to go. You want to fit your model? You just call the fit function. LUZ handles all the loops for you, and if a GPU is available, it automatically uses the GPU, so you don't have to worry about it. It's all taken care of for you, nothing special you need to do. So as deep learning, let's turn to boosted trees, particularly xgboost. It is a great algorithm for doing predictions, and it has GPU capability. Though not on CRAN, you need to install it yourself using pre-built binaries. You download the binary from the GitHub repo, you install some other R packages you need, and then you install this pre-built binary, which has GPU capability, using rcmd install from the command line. You used to have to install it yourself with CMake, and luckily you don't have to anymore, and I want to take partial credit for encouraging them to do this. I put up a GitHub issue, and they very quickly made it happen. And that's what's beautiful about open source. If you ask nicely, you sometimes get what you need. It's really great. So we build another recipe. We no longer need to do imputation, and our outcome is now a zero-based integer. We then build our input and output matrices, and since it's XGBoost, we get to use a sparse matrix for the inputs, which could speed up computation time and can make it take up less space in memory. Since it's XGBoost, we need to build a special xgb.d matrix object, which holds your predictors and your outputs together in one object. And then we can fit the model with xgb.train. And all you need to do to flip this over to using the GPU instead of the CPU is say tree method equals GPU hist, and GPU ID equals the ID of your GPU, in this case, the 0 of GPU. That's it. Now, this is a boosted tree, so the trees are still grown sequentially, but within each tree, the search for the best splits can be done in parallel on the GPU. The issue with XGBoost is you have so many parameters you need to tune. You need to tune all of them, find the best of them. So we'll look at tidy models, which will let us do that which will handle that for us. So first, we need to do some boilerplate. We create the k-fold cross-validation, right here, the v-fold cross-validation. We then use parsnip to set our model specification. We're using boosted tree, and we're tuning over trees, tree depth, and sample size. And then when we set the engine, we can pass engine-specific parameters into the model. In this case, params is for XGBoost, and it has an option tree method GPU hist like we just saw. We then set up our recipe, and for tidy models, it expects it to be a factor for the outcome. We combine the recipe and the specification into a workflow. I update the parameters because I don't like the defaults. And then we set up a parallel CPU cluster. And then we call it Tune Grid. So there's now 2 levels of parallelization. You iterate over the tuning parameters on the CPU, and then each time you fit the model, you do that on the GPU. So we're parallelizing both the CPU and the GPU to get massive speed up. When I did this for the first time, I texted Max Kuna, hey, look, I used both the GPU and CPU in parallel with tiny models. And he said, oh, great, someone asked me if that was possible. I'm the person who asked him if it was possible. So I'm glad it works. So now we turn to Bayes. And once again, this uses OpenCL. Run anywhere coded. And thankfully, the Stan team has done all the work for us. This time we install the CLinfo Linux library, and we find out where our platform and our device are both NVIDIA CUDA. It's NVIDIA CUDA platform and NVIDIA GTX GPU. But we don't use rstan. We use a newer package, command stan r, which is not on CRAN yet. So we install that from the stan repo. Then we use the command stan r package to install stan itself. And I use 4 cores to make the installation go faster. I write a standard logistic regression using stan. But instead of using Bernoulli logit as my outcome, I use Bernoulli logit GLM, because that takes better advantage of the GPU speedups. When I compile, and yes, you compile your stan models, I set CPP options to say use OpenCL. I then fit another recipe, because now my outcome needs to be 0, 1 again. I put the data into a list for stan. And then when I do my sampling, I say OpenCL IDs equals the vector 0, 0, the 0 with platform and the 0 with device. And now all the matrix calculations will be done on the GPU. I'm still doing 4 parallel chains on my CPU in parallel, and I'm doing all the matrix calculations on the GPU. Now this takes up a lot of GPU memory. So we have 4 chains, we're doing all these calculations on the GPU. So make sure your GPU is big enough. But we can get a pretty nice speed up now thanks to 2 levels of parallelization. It's really, really great. So we learned a lot about what we need to do. The first is that CUDA is the linchpin. It all depends on having CUDA installed. And it is very hard to work with. So I highly recommend using Docker if possible, or even better, a cloud VM that's all set up for you. And there's not a lot of GPU-enabled packages left on CRAN, so you have to do this yourself. In terms of custom programming, you're pretty much going to stick to matrix algebra because that's what GPUs are great at. And I recommend just using Torch. Life will be better if you just use Torch. That was the easiest way for me to work with it. And when you want to fit machine learning models, you're going to want to use pre-built binaries. And you should really use Docker. Life is better if you use Docker images, pre-built ones. And it's fairly easy to switch from a CPU to the GPU. It's usually just an option that you need to change. It's not so bad. But your speed gains may vary, so you need to ask, is it worth installing CUDA? Thank you very much. All right. I now have the pleasure of staying on stage to introduce my next speaker. So the next speaker I met about as long ago as I met Kaz.